So in the previous video, we did a very simple design where we had one of these dip switches connected through the FPGA to an LED. So when we change the position of the switch, it turns the LED on and off. And this was really our first attempt at the programming design flow. So if you recall, we built we created this block diagram schematic file, and we created this very simple module called simple with one input, one output, and then we just passed the value of the input, which is coming from the switch, because that pin is associated with the switch, through the module and then to the LED. So this is actually one of the most simple modules you can have in Verilog. But really the importance of the previous video was becoming accustomed with the design flow. So we verified this design, and we did say we're going to make this a bit more complex in the next video. And one of the big advantages of an FPGA is you can actually spread logic across the chip, and all of that logic actually exists in parallel. So it actually, it's actually there as hardware, and you can actually spread functionality around the FPGA to be executed simultaneously. So what we're going to do in this video is we're going to replicate what we have here. Okay, so that's one simple switch going to an LED, and we're going to replicate that 4 times. So we're going to route all 4 of these dip switches independently through the FPGA to 4 LEDs. We've already got one of them, so what we're going to show today is how to replicate this logic and then slowly build the design and make it more complex. So the first thing I'm going to do is I'm going to double click into my BDF, and I'm going to replicate the simple module. Okay, because if you recall last time we have this simple.v, so that's the Verilog file, and what we did last time is right clicked and then created symbol file for current file, and that allows you to put your Verilog file into the block diagram schematic file as a block, which is very convenient because then we can connect input and output pins to interface our design to other things on the board. So I'm going to replicate that 4 times. So that's 1, 2, 3, 4, and then I'm going to create 3 more input pins by simply copying and pasting the other input pins and then connecting them to the modules. So let's just do that one again. Now the first, just going to tidy that up. It's very easy to get sort of tangled up in the wires with quarters. So the first one is called switch. So I'm going to call the second one switch 2, the third one switch 3, and the fourth one switch 4. So just so we know what they are when we go to the pin planner. Then I'm going to do the same thing for the LEDs. So LED 2, LED 3, and LED 4. Now at this point we've updated the design, but you can see we still need to make the pin assignments, because what we want to do is make sure the input pins are coming from the other 3 dip switches, and they have their own specific pin assignment on this board. And you can actually look in the user manual, as we did last time, to find out which pins they're assigned to. So you can see the one we've already done is M1, so that's the one we did in the previous video, and the LEDs, we've got A15, already, which is LED 0, which is the one you can see lit up here. So what we want to do is now update these other pins with the appropriate pin assignments. But before we do that, we actually have to update the design using analysis and elaboration. So it's always worth going back to the block diagram of the design flow so you know exactly where you are. And if you look here, you know now we have to do analysis and elaboration again. So what I'm going to do is save. We know that block.bdf is the top level entity. So I'm going to go to processing, start, analysis and elaboration. And it's going to do a very quick check of the code, but most importantly, it will update the pin planner so these pins are actually showing, and that will allow us to update the pin assignments. So that is complete. So I'm going to go to assignments, pin planner, and you can see those pins are now there. So let's update the pins. So LED2, well, the next LED is A13, B13, and A11. And then the second switch is T8, B9, I don't think it's case sensitive, so that shouldn't matter too much, and then M15. So that should have updated our pin assignments. So I'm just going to go File, Close, and then the next step in the process, well, as you can see, those pin assignments are now associated with their pins, which is quite helpful. And then the next step is to perform compilation. So compilation is this button. So if there's any mistakes in the design, this is probably where it will be picked up. So let's give that a few moments to do the compilation. Once the compilation is finished, we want to program the board with the new design. So when compilation finishes, it produces a .sof file. That .sof file we need to send to the board using the USB blaster. So I'm going to go to Tools and Programmer. And you can see the .sof file is already here. It's always worth going to the folder, Output Files, and just checking the timestamp. So you can see that timestamp was actually 1 minute ago, so I know that's the most up-to-date, most recent design. It does overwrite the previous design unless you rename it something that's different to the project name. So that looks okay, so I'm going to press Start, and that will program the board with the new design. So, right, let's have a look. So we've already got the first switch in the on position, so let's do the second switch. So the second LED comes on, third switch, fourth switch, let's turn the first one off, second one off, third and fourth. So that seems to be working. So what we've done there is just very simply expanded on the initial simple design by reusing the simple.v module, by instantiating it within the block diagram schematic file and adding the appropriate pins to the design. And with an FPGA, you can just keep on going, keep on adding new logic, new hardware, and really the limit is when you start running out of resources on the chip. It's always worth looking at how many resources have actually been used in a project. And with this project, because it's so simple, it's not actually used any logic elements. So of the 22,000 available to us, it's used 0. And that's because it's not actually doing anything at the moment. It's just routing the wire through the FPGA. So as our designs become more complex, you will see this number increase. And this is a good indication of how much more you can put on the chip before you run out of space. So I hope that video was useful, and I'll see you in the next one.